This is Joe Maciars from A Tutoring Enterprises, and today I want to talk about inversely proportional, inverse proportion, and indirect proportion. These are basically all words for the same thing, and we're going to give you a graphical view of what that same thing is. Alright, let's head over to the graphing calculator, and I left up all the stuff from our direct variation. Well, that's okay. We'll talk a little bit about direct variation for just a quick moment. You might remember that I told you last video, that y was equal to kx was the direct variation, and that we were going to have an equation that was a little bit like this. So in fact, let me get rid of the stuff that I can get rid of, like namely all of this stuff. We're just going to dump all of that, hit the little delete button, and now we don't need M and B, so we'll get rid of that. Okay, now we still need a K, so we're going to take advantage of that, and all we've got to do to change this, and this is what the direct variation equation looks like. It's basically a line that goes through the origin, as we mentioned, and the K is the slope of that line. In this case, the K is 2, so our slope is 2. That means if we go over 1, up 2, there we're at the line again. And if we were to go over 1 another up 2, well, it'd be up here somewhere, but we'd be on the line again. All right, so let's go ahead and turn this into an indirect proportion. And it's going to be really different from what we were just looking at, and, well, kind of wildly different. And there it is. It's, well, it's a lot of things. But this is, number one, as advertised, this is our indirect proportion. And it's also going to be our simplest rational polynomial that we can do. We're going to talk about some of the features of that starts to lead us into rational polynomials. In fact, that's really why I'm doing this video, is to head over and start to talk about rational functions, rational polynomials, those kind of things. So let's talk a little bit about this. There's some interesting stuff that's going on. If I zoom out, let's go ahead and zoom out, you'll notice that basically the inverse function, this y equals k over x, where right now k is 2, basically it's staying in what we call the first and the third quadrant. Now, I don't think I've ever talked about this, but the first quadrant, well, this one makes sense because this is the place where the x's are all positive and the y's are all positive. So if I pick any point in here, this is a positive x and a positive y, and this is the first quadrant. Now, a lot of people would think, if they were just randomly guessing, and I said, well, where's the second quadrant? They might go down here and say, well, this is the second quadrant because, of course, you'd want to go clockwise, right? Well, it turns out that that's really not the case. In fact, we do the exact opposite thing. Mathematicians go in the opposite direction, and I'll give them this. They've got a really good reason for it, and here's the reason. Suppose that you had an arrow, and that the tail of the arrow was here, the tip was pointing in the positive x direction, okay? Why would we start there as opposed to the y direction? Well, of course, one might expect if we were going to start, it would be on one of the axes. So first of all, it should be on either the x or the y, and it should either be on the plus x or the plus y. Well, there's probably two good reasons to think that it should start in the positive x direction. The first is x alphabetically comes before y, so you might, given nothing else, you might think, well, let's put it on the x because it comes first. But the other reason is that when you were back in second and third, maybe even fourth grade, you did one-dimensional graphs. Now, I haven't been showing any of those one-dimensional graphs, but the one-dimensional graph was just literally the x-axis. There was no y-axis. And so, since that is what you started with first, you might also think that, well, that's the direction I should put the arrow. Okay, now, given that you've got an arrow that's on the x-axis, pointed towards the right, and you wanted to start to move that arrow, that is rotated about the origin. So you're either going to move this way or you're going to move this way. Which way would you go? Would you go into the place where there's positive x's and positive y's, or would you go into the place that had positive x's and negative y's? Well, yeah, probably you'd go this way. And not only would it make sense to go this way, but you're always also going towards the y-axis. All right. Now, let's suppose you got your arrow rotated 90 degrees, so you went all the way up to here. Your arrow's now pointing straight up. Would you suddenly switch it into this quadrant, or would it make sense to just keep on rotating and go into this quadrant? Well, of course, you'd like a nice smooth rotation, so you go up to from your x to your y, and then you would start heading down to your negative x. That, at least, I mean, I've never been told that that's the reason, but it makes sense to me that that's what the reason would be. So this is our second quadrant right here. This is our third then, because we're going counterclockwise, and this is our fourth. So it's 1, 2, 3, and 4. All right. So based on that, we can see that our inverse function here, our indirect proportion, is in the first and third quadrants. Now that's not a requirement, but it is the case right here. Now the other thing we can see is that it appears that the red lines start to approach the x and y axes in their quadrants. And one might suspect that no matter how far you zoom out, and let's do a couple more, they never really go into the other two quadrants. Well, it's a little tough to see because now we're getting to scales where, what if it went up just a little bit and then came back down, or actually went down a little bit and just came back up? What if it snuck in there and we didn't know it? Well, yeah, okay, you might argue that it might be able to, but you can actually prove that it won't. So right now, this particular function is in the first and third quadrants only. And by the way, and we've talked about this before, the red curve actually never does touch the black lines. Now it does here. It's being graphed here because when you get to faraway points, a pixel has to be colored. So you can either color the one that's below the line or the line itself. Well, once you get within a certain distance, the 2 pixels have to end up being colored the same. So yes, here on the graph they're actually colored the same, but mathematically the red line never actually touches any of the axes. All right, so that's a feature of this graph. Now, let me zoom back in, and I'm going to show you how we're going to indicate that feature. In fact, instead of having red, let me go ahead and change this to green. I likes the green. Let's do the green. All right. Now, let's put in y equal 0 because that will be one of the asymptotes. Now, you can't see it right now because it's black, but I'm going to go ahead and just type in x equals 0 right away because then I'm going to color them both at the same time. It'll save me a little time. So let's highlight them both, come back up to our inspector. We're going to color it red. There you can see them popping up underneath. And typically asymptotes are dashed. So I'm going to go ahead and dash them. It actually makes it look kind of ugly because they're right on the axes, but we're going to live with that. Okay, so there it is. There is our indirect proportion, our inverse proportion. We could say that the variables x and y are inversely proportional. By the way, if I were to do another equation, which is basically just multiply the x over here, then we would have something like xy is equal to a constant. Now that constant in this case is k, but you can see there it really is the exact same equation. And this graphing calculator has no problem graphing it in this form. So, but let me get rid of that. I just wanted to point that out. All right, there's one thing left to do before we end this video, and that is to actually play with k a little bit. There's really not much else to do with this. We're not going to look at this as a rational function that we can move around. I'm going to do that in the next video. But let's go look at what we can do with k and what happens to it. All right, so we're going to animate the parameter. You've seen me do this a lot of times now. Let's keep it to -4 to 4. Let's do that. And 41 sounds good to me. All right, so let's hit the OK button, and without further ado, let's play it. Well, that's pretty anticlimactic. Paused for a little bit, but there it is. Okay. That's kind of cool. Notice we're now in the second and fourth quadrants. And boom, there we're in the first and third. What's going on? Well, let's look at the k value that's happening. The k right now is a positive number. We're headed towards 0. Oop, there's 0, and now we're in the negatives. And back into the positives. Okay, So basically, we can say that this indirect variation equation is in the first and third quadrants when k is positive, and second and fourth quadrants when it is negative. Now, just to highlight this particular point, you'll notice that what the graphing calculator is doing when k is equal to 0, basically we're getting a line down here. It's not drawing. It looks like it could have also been a line this way, except for one detail. Because of the graph that I'm actually, or the actual equation that I've written down, this equation cannot allow x to be 0, and that's why you're not seeing that. Had I gone ahead, in fact, let me go ahead and just change it. If I go ahead, I think this is going to work. Let me go ahead and just multiply x times y and say it's equal to k. That's like that other one that I just showed you. And let's see if it'll show, change the color on me again. So let's go back, and I want green. Okay, and I missed it visually. Let's see if we're going to get a vertical line. I was kind of expecting we would. Let's see it. Yeah, we got it. Okay, let's go take a look. Now, there's no restriction on x being 0. Let's go ahead and pause this, make k 0, and now it doesn't matter what's 0 because either one can be. So there is a subtle difference between this form and the previous form where x cannot be 0, but often you're not really interested in the situation where k is equal to 0. So it really doesn't come up as an issue, whether you're really talking about this one or you're talking about the other one. It's going to go back to the ugly black color again. So one more time, we're going to color it. Kind of giving me a hard time today. All right, so there we go. Okay, and let's play it. Now, there is something of a little bit of interest here in terms of, in fact, let's zoom, see if I can get some nice numbers. Yes, those are some nice numbers. Okay, and I'm talking about these numbers here and these. You'll note, let's go ahead and pause this. If we go ahead and make k1, you'll note that this shows me that when x is 1, y is 1. And if I make k4, that would be a good one, which is the very end, okay, then I've got a situation where x could be 2 and y could be 2 to get to this point. Now, later on, we're going to be studying some conic sections, and this, I told you this particular function was basically in a lot of different things. One of the things it's in is in the indirect proportions. Another that it's in is in rational functions. We're going to study that next. But a little after that, we're going to study conic sections. And this is actually a conic section as well. This is a hyperbola. And if you've studied hyperbolas, you may not be used to looking at them in this orientation, but this point and this point are the vertices of the hyperbola, the branches of the hyperbola. And there's actually a box. The box is at a 45-degree angle. Don't worry if you don't understand what I'm saying now. If you haven't studied hyperbolas, it's just for people that at this point understand that. I will show you that in another video, so don't worry about it. But the point is that this particular equation shows up in a lot of different places, and we're going to study it quite a bit. Another thing we can talk about is the transformation. We can kind of think of y equals 1 over x as the parent function for inverse functions, and k then represents a stretch. Yeah, okay, but a stretch in what direction? Well, typically that stretch is associated with the y value. At least I think most people would associate it with the y value. I guess I'd have to maybe take a survey of teachers or something. But the truth is that this could actually be set up with the y or the x or with both. And let me just show you that. Right now, note we have the equation y equals 4 over x. Okay? So if I type in y, I guess, well, here's what I want to do. I want to type in x over 1 times y over 1 equals 1. Okay. Now that's going to give me that one function that went to here. Okay, this is the quote-unquote standard one. Now, what I can do to represent a stretch in the y direction is simply go ahead and change that 1 to a 4. Okay, and if I'm right, you're going to see the black curve now switching to being on top of the green curve. Let's see if that's right. There it is. You see how it's on top of it? Okay. Now, that represented this single point going up 4, so it's off the grid. Let's see, a point that would have been here. Let's go back and change it so you can look at maybe a smaller point. Convince yourself. Well, here we have the point 2 1/2. We know this is exactly 1/2 because k is 1. But what happens to this when I change that 1 to a 4? Boom, comes up to there. So this is actually, now we're thinking about this as a stretch in the y direction by a factor of 4. But that's not the only way we can do it. Let's go back to this. Okay? And what we're now going to do is we're going to look at this point. Notice that this is 1/2, 2, which is also on the line. And we're going to think about this as a stretch in the x direction. And you'll note that to do that, all I got to do is change the 1 that's underneath the x into a 4. And lo and behold, I get the exact same thing. All right. Now, that's not the only way I can do it. I can actually stretch a little bit in the x and stretch a little bit in the y. That is, again, let me go back to 1, 1. Let me take this point, stretch it this way, let's say in the x, and then take it and stretch it in the y by factors of not 4, but 2 each. Let's do that. 2 and 2. Notice that 2 times 2 is going to be 4. And so there it is. And I can play this game, as much as you like. I can actually think of, let's see, this is a stretch in the x direction as of 8, and this is a compression of 2, or a stretch of 1/2. And I should get it to lie on top of itself. And of course, it has to be, because 1/2 of 8 is still 4. So it's sort of interesting that this is something that you can view multiple ways as stretches in many directions, many different kinds of combinations that get you the same curve. And this is one of these kind of weird symmetries, and I haven't actually studied this in a specific class. I'm sure there's somebody that studied these kind of things and there's a word for it. There's some sort of scaling symmetry or something. And maybe if somebody who has enough knowledge, sees it, you might want to point me to maybe a video or a book or something that I can go look at. That would be wonderful. And when I get a break, I'll go ahead and actually read it and pass along the information to my viewers here. But basically, it's interesting that we can look at this as stretches or dilations in multiple ways. We're going to also have another video in the future where we just talk about all the geometry things, the transformations, the shifts, the dilations, and the, what's the other thing? The rotations. We're going to look at those kind of things. And we're going to connect them to algebra because, quite frankly, the textbooks don't tend to do that very well. And I'm going to kind of bridge the gap from the littlest things that you learned in the basic algebra up through geometry and all the way into something like linear algebra, which is basically learning some matrix theory and showing you how that all works. Okay, I've talked a lot, and I think that's enough for today. Let's go ahead and get out of here. We're going to go look at the end screen. Those of you that have seen a few of my videos, this will not be a big surprise. We were studying inversely proportional equations, inverse proportion equations, indirect proportion equations, and we're getting ready for bigger and better things. My little business is A Tutoring Enterprises. My name is Joe Maciars. That's my website, email, that's my phone number. I do online and in-person tutoring in physics, math, and chemistry, and do some engineering along the way. And if you guys need some help, give me a call or contact me. I'll try to give you a hand, and we'll go from there. A lot of good information on the website about prices and times and things like that. Might look, if the summer's coming around, you might look for summer specials. We might do some of that. I haven't made up my mind on that. But all right, onward and upward. If you like me, I would like you. If you like the video, please like it. Enough said. All right, it's bad. Bad joke. All right, shareware for the brain. if you really like this and it helped you, feel free to send me $1 or two. It's always nice to feel like I'm actually appreciated for some of the things that I'm showing you guys. And if not, well, if I help you in something else, or maybe you need some help in tutoring, you'll take advantage of that. All right, here's a white screen, and in this white screen you should see various links popping up to the past videos, to the future videos. You might even see a few links to other topics. I'm starting to do other kinds of videos, and maybe you'll find some interest in some of that stuff. Well, I really appreciate you checking out this video, and if you made it to this point, I thank you for looking at it all the way through. I hope you have a great day.